Thanks a lot. Can you hear me okay? Great. Thanks so much for inviting me. So this talk is actually going to be a little, a little peculiar in that it's going to be quite short, which I think people rarely complain about talks being too short. Also, it's going to be hopefully not much more than 45 minutes of me talking, and then we can either take a break or whatever you're up to, and then mostly me typing to show you kind of the tool I'm presenting and sort of show you how it potentially it's something that you could be doing as well, which of course is the hope of every tool developer. But more generally than with just Lean, I do want to try and introduce you to interactive theorem proving, because I think not only is it something very useful and something that I'd like to promote in the programming community, it's also something that's super fun. And trying to get that message across, I think, would be more useful than trying to slam you with applications and theory. So for probably over half of my talk, I'll be sitting at my keyboard, hopefully not cursing at it, but at least sitting at it and trying to, with you, sort of interactively develop proofs of some very simple programs. And hopefully I won't freeze out of nervousness being in front of all of you, but it's going to be a live demo, and because of that, I'd really appreciate it if you have questions, just go ahead and raise your hand or ask them or yell them up front, and I'll be happy to answer them. I mean, this is really supposed to be, a way to engage you with this type of thing. Now I'm really dismayed to see that my talk is right in front of me, but it's not up on the screen. So obviously they're not being mirrored. And this is the traditional pre-talk technical difficulty. Also new laptop, which makes everything easier. Let's see. How does this look? Not so great. Oh, much better. Yeah, this looks pretty good. All right. Okay, so I guess I should start with the better introduction, which is my name is Cody Roux. I currently work at Draper Labs, that's in Cambridge, right across from MIT. This is work that I'll say more about when and where, but it's mostly work that I did before being at Draper Labs when I was at Carnegie Mellon. And again, it's mostly about interactive theorem proving and also about promoting some of my work, which is developing an interactive theorem prover with Lean. Again, a point I want to get across before even starting is that interactive theorem proving is really like programming in many ways, but it's also unlike programming in many ways. And really, I like this metaphor. You should see it if you learn to program in C or in Java. You should see learning how to use an interactive theorem prover as when you were learning how to use Haskell, which means it's something that is somewhat familiar because you already know what programming is and what a compiler is and how tools work, but it's also really unfamiliar in that there are things you really expect or things that you really look to find and that you completely don't find, and there's a way of thinking that you completely have to rediscover. And this is part of the fun, but it's also part of the difficulty. And traditionally, there's a pretty difficult learning curve with interactive theorem proving. I want to say steep, but apparently steep learning curves are good things. So, all right. Okay, so here's a complete tautology. Interactive theorem proving is the field of proving theorems interactively. So what you want to do is actually find a way of mathematically expressing certain things, propositions, ideally interesting ones, and then you want to prove them. And computers should be involved as much as is convenient. And the field itself of interactive theorem proving is completely computerized, right? So you completely want to specify your problem using a formal language, which is a lot like a programming language. We'll see that in a minute. And also the proof should be interactive. So the computer should be helping you write this proof. Okay, so that's great. So what are the real, hopes and aspirations of this field? It's a pretty old field. In fact, I remember Martin Davis giving a talk about this. I think it was a variant of the ENIAC, and he programmed a decision procedure for this computer, which barely had, less than a kilobyte of memory, and he programmed a decision procedure which is doubly exponential, we now know, in the size of the input, which I thought was insane, but also kind of inspiring. So one of the aspirations of this field, which again is a relatively old field, is verifying mathematical theorems in general, but where's the money in that? So what you also want to do is verify the correctness of programs. And correctness is a subject I could give a whole other talk on, but in general, we sort of know what it means for a program to do the right thing, and we want to be able to express that thing and show that, yes, my program, as I've written it, does the correct thing, or it doesn't, and then I need to fix it. And hardware verification, of course, is the same thing, except it's much more expensive to repair bugs. So surprisingly, hardware, really unsurprisingly, hardware verification has taken off much more quickly than software verification because it just costs so much more to make mistakes. All right, so this is my favorite part of the talk. So what is this actually good for? So Ron Jeffries, user Ron Jeffries, from one of my favorite sites called c2.com. My favorite site because it conglomerates every possible argument you could have about software development and every religious war you could possibly imagine about language design is all right here in this gigantic, unreadable site. So there's a page on formal verification, and Ron Jeffries says, okay, this is great, nice toy, but really if you're dealing with life and death, you might prove some key algorithm. All right, I'll concede that if somebody's life is in the balance, you might want to try it. But in the real world, and this mythical real world is something C2 users are very fond of talking about, you really aren't going to need it. In the real world, we write web applications. We don't write software that monitors heartbeats. And okay, but who is this user, Ron Jeffries? He's a real person, and I hope I haven't insulted him by citing him here. But there's some sort of more legitimized criticism that comes from some pretty serious computer science scientists, DeMilo, Lipton, and Perlis. And they write a whole paper which is basically saying formal proofs of programs is a completely useless field, and we'd really do better to spend our time doing other things. So they write in their introduction, or in their abstract actually, that the absence of continuity, the inevitability of change, which was already something people were really feeling in 1979, and the complexity of specification of significantly many real programs make the formal verification process difficult to justify and manage. And they take stronger and stronger language in the actual article, where they say basically any hope of proving anything useful about any real program is a waste. It is a waste now, and it will always be a waste, which I love this kind of prediction. Right. So I mean, they do mention some impossibility theorems, which are real, which exist, about what it's possible to prove about programs. But they use that to say that in practice also, these proofs are infeasible. And later on they say, unfortunately, there's a wealth of evidence that automated verifying systems are out of the question. And then some other user on C2 adds the final nail and the formal methods coffin, and says that the amount of formal reasoning required to even prove the smallest program is beyond the capacity of most of us, where most of us presumably refers to the other users of C2.com. And as an optimist, I believe that is false. So, okay, so 1979, these quotes from C2.com are quite hard to date, but I believe they're sort of early noughties. And here's a paper from, darn, I should have sourced the year. I think it's 2012 or 2013. So they're talking about a C compiler that I'm going to bring up later called CompCert. And one of the salient aspects of the C compiler is that it was completely verified in one of these interactive theorem provers that I'm going to show to you a little bit later. And it's called CompCert, and it is one of the great achievements of this field. And they say, so they developed a fuzz tester for finding bugs in compilers. And one would think that compilers that have been around for 30 years or 50 years either are practically bug-free or have extremely difficult to find and obscure bugs. This paper shows that that is not the case, this finding and understanding bugs in C compilers. I highly recommend reading that paper because it is brilliant. They use a fuzz tester. They find a wealth of very subtle bugs in C compilers all over the place, tons of bugs. Some of them that are still not fixed just because GCC is a horrible mess that is extremely difficult to change. And they do say this about CompCert, which is the striking thing about our CompCert results, is that the middle end bugs we found in all other compilers are absent. As of early 2011, the under development version of CompCert, which is now not under development anymore, of course it's still under development. Yeah.
When you're done with reading this and making your point, can you just explain what they mean by middle end bugs?
Yeah, I will, and it's a good question. Is the only compiler we've tested for which CSmith cannot find wrong code errors. It's not for lack of trying. We've devoted 6 CPU years to the task. The apparent unbreakability of CompCert supports a strong argument that developing compiler optimization within a proof framework where safety checks are explicit and machine checked has tangible benefits for compiler users. And I love this sentence. It completely destroys the conclusion of de Maillipt and Perlis, which of course makes me very happy. And I really like when people make solid negative predictions about this is never going to happen, it's too hard. And then later you can come across something that says, we've done this, and it is in the realm of the possible. It's quite exciting. So basically they're saying that the middle end bugs in CompCert are non-existent compared to the dozens, and I can't remember if it goes over 2 digits, dozens of bugs in all well-developed C compiler frameworks. All right, so what does middle end mean? So they did find some bugs in CompCert, and those bugs were, if I remember correctly, which I probably don't, but some of them were connected to parsing and in particular inserting casts, which is part of the front end's job of inserting explicit casts. And this is quite subtle, actually. Everything about C is quite subtle, actually. So anything that was unverified is subject to bugs. And this is ridiculous to what extent this is true. I mean, you really think that, oh, this isn't completely true, but it's simple enough. We probably won't find a bug in here. We don't need to verify it. Almost invariably is followed by, oh, actually, we found one bug, and it was in this unverified part. So this is really what happened. There's some unverified parts of CompCert, which is unsurprising given the scope of the project. Certainly at the time they were unverified. Today I think those parts are verified, partly because of these results. And the unverified parts did have bugs, and it was part of the front end, the desugaring, parsing, and macro expansion. I think macro expansion is hopeless. That's still unverified. So when they talk about middle end, it's once you have the AST, all the optimizations that are done after that. And some of those are actually quite subtle and quite complicated. Not all aggressive optimizations are done in CompCert because every optimization you do has to be verified, and that's a lot of work. But the ones that are non-trivial and are verified. Yes, I'm sorry.
So what is CompCert and what is C-Smith?
So CompCert is the subject of the point I'm trying to make. It's a C compiler that's been verified and that is surprisingly bug-free. C-Smith is a framework that is used for testing compilers. So it randomly generates syntactically correct C programs and tries to modify them in a way that preserves their semantics, and then it runs them through a compiler and sees if basically they do the same thing, which they should, of course, if the compiler is correct.
So CompCert is different from GCC?
Yes. CompCert is an alternative to GCC in some ways. It supports a smaller fragment of C, but it has this incredible level of trust that you can attribute to it. So it compiles a subset of C11 and I think all of ANSI-C.
Modifications to the program done through AST transforms?
I'm sorry.
Just mentioned something that modifications to the program is
Yeah, so CompCert takes a string, turns it into an abstract syntax tree, and then it does a bunch of stuff, including turning it into a number of intermediate language and transforming those in many ways.
But it's operating on AST.
Yeah, as do all compilers. And I think there was a third question on the left.
Yeah, that's actually a very dumb question. How come you didn't verify that there are no front-end bugs either?
So they did. It's just, to be honest, and this is the anti-sales pitch. This was a humongous effort. And in 2011, it certainly wasn't finished. And it required, I don't know, easily 10 or 15 man-years. So by 2011, a lot of things were unverified. Some things are hard to verify, and most notably, those things are what did the specification writers for C intend? And that's, I mean, no amount of formal reasoning can solve that question. The intent of what the specification is a real big problem when you're translating it into formal language. But it has the advantage of forcing clarification at that point. So I think this CompCert verification, one of the good things that came out of it, one of the really good things that came out of it, other than just a compiler, was the fact that people sat down, took the C specifications, and turned them into formal specifications, which are much more precise, much less ambiguous, and usually more complete. In particular, it's easy to forget corner cases, and formal specifications usually are corner case resistant, if not immune. Were there other questions? I'm afraid to say I don't know about CompCert as much as I'd like to, so some CompCert specific questions I might not be able to answer. Yeah.
Like subsequent work, sort of, as if this is like maybe go after this, like, this is possible, where they're like, we
Yes, but C is a real language. It is a complicated language, and certain aspects of C are quite, quite nasty. So the fact that it's a real language, the fact that it's well used, well understood language with lots of features, and this is an optimizing compiler, I think puts CompCert in a unique category. Unfortunately, it'd be nice if we had a verified Haskell compiler. It'd be great. But again, the amount of effort involved is really non-trivial. Okay, so here's the actual sales pitch. I probably should have emphasized CS more, but I really like math, and so the math verification milestones are quite nice. So you take these tools and you say, okay, well, what can we formalize in it other than toy theorems? And this is an important question if we want mathematicians to use it. And I'm sorry, I'm gesturing to this one since earlier, whereas they asked me to gesture to this one. I'm very sorry. All right, so so if you want adoption by mathematicians, you have to show them you're serious. And to show them you're serious, you have to formalize a non-trivial theorem for a mathematician. That bar is significantly higher than what I would call a non-trivial theorem. But in the last few years, it's really been coming along. We've seen some really impressive formalizations. In particular, one of the most famous, top of everybody's slide, is the four-color theorem. So in the mid-'70s, I can't remember the year, this famous conjecture that every map that doesn't do stupid things like add islands in the middle of lakes in countries, every map that's reasonable can be colored with only 4 colors. Now, it's okay. Won't go into the history, but it's a bizarre fact that showing that this is true for 5 colors is reasonably easy. It's a couple pages of proof. Showing that it's possible with 4 colors is extremely hard, and this question was open for hundreds of years. It was finally resolved by some brilliant mathematicians, which showed that you could reduce the problem to a few hundred cases, and then those cases were quite huge, and you had to check them all to show that they actually were 4-colorable. And they did that with a computer, and at the time, it was quite an achievement, but there was a lot of discomfort about this proof because it relied on a large amount of code, which, as you all know, n lines of code is 2n bugs, and so you had to trust, this code that ran for several weeks, on specialized hardware, and it prints out 0, which is like yes, and it's, well, it just seems kind of hard to trust. And of course, the proof itself was quite long. But it wasn't unfeasibly long. People trusted the paper part of the proof. They didn't really like this computer part. And so this seemed like a pretty good challenge in 2005 for Georges Gontier and, to a lesser extent, Benjamin Werner, to formalize these computations themselves to make sure that they were actually computing what people thought they were computing, and while they were at it, formalize the rest of the paper proof, just to be able to say something really nice at the end, like, here is a statement of a very simple fact. Every map can be 4-colored, and here is a huge, 10,000, or I'm sorry, 100,000 line program which embodies an actual mechanical proof. I'll say more about exactly what this means later, but the basic point is that this sort of completely unfeasible thing that they're talking about here is exactly what they produced here in 2005 for the 4-color theorem. It is a complete, incredibly detailed proof of the 4-color theorem. So once that door was open, there were a lot of really nice results that were formalized. One of them is the prime number theorem, which is sometimes called the fundamental theorem of number theory, which I think is beautiful and which is really quite hard to understand, even for an undergraduate in mathematics. At least the proof is. The statement is not so hard. It basically says if you go to really, really large n, the number of primes that you can expect to find under n grows like n divided by this correction factor, which is log n. So basically, there are almost as many primes as there are numbers, but there's this sort of log n fewer primes as you get larger. It's expected that primes eventually sort of peter out because there are so many more ways to factor things, but they don't peter out that fast. And in particular, log n, 1 over log n goes to 0, but not very quickly. So this ratio of primes to non-prime still is pretty big. And this is the crowning achievement of 19th century mathematics. The proof is horrible. It uses complex analysis, which I hope you've never had to cope with. But yeah. Yes, I think your question was Erdős and somebody else, I think Selberg, managed to find a proof that didn't involve complex analysis. And so they called it an elementary proof. The proof is unreadable. I don't recommend reading it. But it was convenient because it led to a formalization of this proof, a complete formalization in the same sense as the four-color theorem, but this time in Isabelle, which is a very related but different system. And now the really important, the really the hard hitters of these examples are the two last ones. So the Feit-Thompson theorem. I'm not going to go into the detail of what this theorem says, but it basically talks about finite groups, which maybe you've heard of. Basically, a group corresponds to some kind of symmetry, and it says something about groups of odd order, so groups whose size is not divisible by 2, and it says that all of them are solvable, which is a kind of way of saying they're all relatively simple to understand. This proof is over 200 pages long and is quite technical, 200 pages of graduate mathematics. It is one of the first proofs I've seen formalized that I think you could find mathematicians which would say, yeah, I'm not sure about this proof. It's just really hard and really long, and it relies on many different results. So this was really a milestone, and Georges Gontier and his team of extremely competent people managed to produce a completely formalized proof in Coq. And basically, as a side effect, they formalized a whole undergraduate course on algebra, which is also quite an achievement. An equally impressive achievement was Thomas Hales, who solved one of the oldest open conjectures at the time, called the Kepler conjecture, which is basically how to pack spheres in the most compact way. So it's kind of hard to state formally how this works, but the intuition is pretty simple. You take a bunch of oranges, you have a crate, you want to fit as many oranges as possible in the crate. You sort of try and do it so that there's the least space between the oranges, and you'll come up with something, and that something is the sphere packing in dimension 3, and there's a nice way to express what that is, and it is much harder, but also possible to prove that that is the best possible way you could pack spheres, all right? And this was an open question for a very long time, and it was a very actively open question from basically the 19th century on. And finally, it was solved, again, a lot like the four-color theorem, where you said, okay, here's a bunch of finite things we need to verify, certain little inequalities, and there's 100,000 of them. And if they all hold, then so does the Kepler conjecture. So here's a giant program that runs through all these possibilities and tries to solve them, and it uses floating point numbers, and it's terrifying. And so again, Thomas Hales, crowning achievement of his life, prove the Kepler conjecture. I shouldn't say that because he's still alive. Extremely important achievement of his life, prove the Kepler conjecture, and the reviewers came back and said, we tried really hard to understand this proof. We're reasonably sure about the paper part, even more sure than usual about proofs. But this program, like, we relatively believe that it works, but you know, we can't say anything. We're exhausted, we're done. And Thomas Hales kind of felt cheated, understandably, because this was, you know, really significant result. So he said, okay, what I'm gonna do is I'm gonna take 10 grad students and 10 years, and we're gonna formalize this completely in some theorem prover. And that's exactly what he did, which I have to admit is extremely admirable. I don't know if I have that kind of drive. And this is a quite recent result. I mean, it was announced end of 2014 that they had finally completed this completely formal verification of the Kepler conjecture. So these are the mathematical big hitters, and it really says something in the sense that you take a proof that no reviewer had said, I trust 100%, that was hundreds of pages long, that was extremely complicated, that was extremely you know, specialized in the field. You take an expert that didn't know anything about formal proving. He decides to completely formalize this extremely difficult proof, and he succeeds. All right, this is kind of where we're at now. Someone who's very motivated can formalize almost arbitrarily complex pieces of mathematics. Now, there's a complex argument about how how much actual work it would take to formalize, say, the proof of Fermat's last theorem, and this is a complicated debate. So let me move on to the CS accomplishments. One that is at the top of every slide in formal verification is the Metro 14 line, which is completely driverless. You can imagine what kind of nightmares a driverless metro line would pose to security. I mean, this is one of those loss of life situations. So they decided to go a different route than usual, and instead of doing extensive testing, they would still do extensive testing, but not quite as much, and they would rely on formal methods to try and verify certain security properties about this driverless metro. And it was a success. As far as I know, there have been no safety critical bugs on this metro line since its operation. Of course, I've talked about the CompCert C compiler, which is the real crown jewel, which is a complete formalization of a realistic compiler for a realistic language, which is extremely robust. But one I think is even more impressive is this SEL4 microkernel. Unfortunately, I don't know quite as much about this one, but yeah, basically you take whatever springs to mind as the most incredibly complex and hard to specify piece of programming, which is an operating system kernel, and you build a full one that's completely verified. Interestingly, they used Haskell for this, and from the Haskell, they derived formal verification conditions that they verified in Isabelle about timing, about privilege. And on the other hand, they used the Haskell to generate C code, and that C code formed the basis of the implementation of the kernel. The kernel is technically written in C, but it's generated from Haskell. That's a good question. Yes, I do believe that they have a formal proof that the generated assembly or C is somehow correct with respect to right. Yeah, I also recommend you look into this, if possible, more than I have.
Is there a problem? Isn't there a problem in provability? Like Rodin's theorem?
Yes, so there is an issue in provability, which was, again, already mentioned in this perilous anti-formalization paper, which is basically some things are true but unprovable. Now, you first have to notice that mathematicians don't worry about that so much, right? They know that some of the mathematical theorems they try to prove are unprovable in a given, formal system. But that doesn't keep them from trying to prove it, and it really doesn't keep them from often succeeding. And the situation is kind of similar here. You have a program or a mathematical statement or, I don't know, a statement about social science that you somehow managed to formalize using one of these specification languages. And now you ask, well, can I give a proof? And the answer is overwhelmingly yes, if it is a true theorem. In rare cases, you have statements which are unprovable. And there are some cases where we don't know because we haven't proven them yet, so they might very well be unprovable. But in most cases, not only, I'm sorry, in most cases, you can solve them one way or another. And if you can do that, you can do it in a formal system. And if you can do that, well, then you can formalize the proof. Now, remember that all these proofs are written by the human, all right? Perhaps, and I'll go more into this, with the help of the computer, but they are written by a human. So, so one thing we don't have yet is a program which knows how to prove complex statements about mathematics automatically without human intervention. But that's more of an AI problem, I feel, than it is a philosophical limitation that comes from Gödel's incompleteness theorem. So I really do believe that there are, there are two issues here. How good can programs do things that humans do? And what are the unprovable statements of a certain formal system? And I think the second problem is an interesting philosophical problem, but in practice, it arises very rarely. If you have a program and it works, then you probably have at least an informal intuition of why that works. And if you put the work in to formalize that intuition, then you can write down a proof, and you can get one of these, bullet points. Does that answer your question? All right. Unsurprisingly, people that are interested in formal proof are also, of course, fascinated by Gödel's incompleteness theorems, and so these questions come up a lot. In particular, the first incompleteness theorem was formalized. It's not in one of my bullet points, but the first incompleteness theorem itself was formalized several times, and the second incompleteness theorem, which is incredibly hard to formalize, was formalized quite recently by John Harrison, I believe. So, people have been thinking about this. Okay, enough sales pitch. I'm almost at the end of my first part. So how can you actually get started with theorem proving? All right, so this is now the personal segment where I'm going to try and get you interested in actually downloading this and trying it out, and hopefully not giving up and saying this is rubbish after 10 or 15 minutes. Okay, so actually I'm not done with my sales pitch. So I've been talking about some of these systems, Coq, Isabelle, and HOL. I'm not actually going to use my examples with any of those systems, but talk about our new and improved system, which is called Lean. And it's developed by several people. I'm not going to cite them all. The main developer is Leonardo Demura, who works at Microsoft Research, and Sunho Kong, who is still a PhD student at CMU. And the main developers of the library are Jeremy Avgad and his student Floris van Doorn, who are also at CMU. But of course there are others, including to a certain extent myself. And the prover itself can be found here, right there. You don't have to remember that by heart. What's that? Yes. So I would recommend you to follow the installation instructions on this page because it is quite sensitive to those installation instructions. They do, but there are a number of dependencies that you have to be careful about. All right. So yeah, it does work. It is quite robust to surviving installation. These slides are online, so I'll leave this for another second if you're actually typing this in right now, but otherwise, yeah?
Have there been any significant like negative milestones where you think something's working properly and it's
So a negative milestone where something you thought it worked and then it was disproven. Okay, so this is a difficult question actually, an interesting one, but a difficult one. So one thing you would expect is that as you formalize things, you find critical bugs. One example that comes to mind, though I would be hard-pressed to find a citation for it, is they tried to formalize the soundness of the Java type system. So they didn't actually do Java because that's too hard. They took something called featherweight Java, and they tried to formalize the soundness of the type system there. And they failed. And the reason they failed is because the Java type system is unsound. And so that's one example of what you say. However, I have to admit that in general, these examples are hard to find because in general, what you want to do is something that's not too hard, and in particular, verifying the system after you've built it is excruciatingly hard and quite frustrating. And I would tend to say pointless. What you should be doing is formalize and verify and develop all at the same time. So while you're developing, you write formal specifications and you verify that you're conform to those specifications. If you do that, then you will find a multitude of mistakes you made in your ideas of how things were going to formalize. It's going to happen all the time. But the end product itself, because you've been doing this completely continuous development, is going to be sort of by construction free of these kinds of surprising bugs. Okay, so here's the background. All right. So I was scared I was going to run too short. Now I'm scared I'm going to run too long. I'm not going to, I promise. Okay, so what's an interactive theorem prover? It's a theorem prover that is interactive. I was trying to be clever here, but more seriously, a theorem prover really needs to be able to take specifications, verify that they make sense, and take proofs, completely fully detailed proofs, and verify that they are actually proofs of the theorems that they pertain to be proofs of. All right? So it's just basically a tool that takes a program, that takes a specification, a proof, and answers yes or no, and hopefully gives you a little bit more information than that. All right? So it's something that verifies completely formal proofs. Now, completely formal proof is something that we understand now. All right? Since the early 20th century, people have been trying to understand this philosophical question of what is a proof. And in an extremely rare case of actually solving a philosophical question, they succeeded. They completely succeeded in giving a definition of what we can reasonably expect to be a perfect formal proof. So this is, again, unprecedented in philosophy, is actually succeeding in answering one of these questions. Usually what happens is you have a philosophical question, you answer it, and in the course of answering it, you create some scientific discipline. And this is really what happened with formal proofs. So we know what formal proofs are. We've known since the start that formal proofs are incredibly detailed and hard to produce. And at the time, mathematicians reacted a lot like reacted in the early 1910, a lot like computer scientists reacted in the end of the 70s, which is to say, these proofs are nice little things, but no one is ever going to create one. It's just too much work. And before computers came along, that was true. But now we know how to verify proofs completely just automatically. So the first element of a theorem prover of an interactive theorem prover is a kernel, which is to say something that can take a completely detailed proof, say, yes, this is indeed a proof of what you said it was, or no, it's not. And that, and I'll get more into this later, is something you need to be able to trust, all right? Because that person is sort of the last line of defense against proving things that aren't actually true. And the interactive part of interactive improver is, well, everything else, right? I'm sure a lot of you have used Eclipse at one point in your life. Eclipse is a crazy, gigantic, difficult to learn tool, but it is a very powerful tool. And that is because it basically provides you with an interactive way of developing programs. And so what you want here is an interactive way of developing proofs. In particular, you don't want to write those full detailed proofs yourself. You really don't. They're horrible things. You never want to see one of those. What you want is something called a proof engine, which basically asks for clues, as few as possible, and in the end returns one of these completely full detailed proofs. Also for specifications, it turns out that writing full detailed specifications is also quite hard. And to relieve that burden, we have something called an elaborator. And I won't go into as much detail, but the elaborator is a quite important component. And in particular, it uses a lot of interesting ideas, including things like type classes and something called hierarchy unification. And surprisingly, or maybe unsurprisingly, the elaborator and the proof engine really need to interact and have a lot in common. Okay, so two silly examples, just to seal the deal, is the ideal prover.
Are you going to show some code eventually?
Yeah, of course. Yeah. All right. Maybe I'll skip through some of that stuff, but I will definitely show some code. This is really the point, is to sort of say, oh, and actually it works. Okay, so the ideal theorem prover would be somehow super powerful logic, and the proof engine is just a button that you push, and it says yes when it's true, and no when it's not true. This, of course, does not exist. The simplest prover is some simple implementation of logic, like first-order logic, and then the engine would just be a parser, right? It just says, give me a complete, full detailed proof, and I will check to see if it's actually a proof. This is already non-trivial to implement. It's not hard, but it's not trivial. But this is too simple. It's kind of unusable. So the reality is somewhere in between, where we have an engine that does a lot more than just read proofs. It tries to help you. Our logic is something between an extremely simple baby logic and an incredibly powerful, unusable logic. And then the user has to do a lot more work than just press prove, but a lot less work than write a full proof. Okay, so the kernel itself is really the last line of defense against proving falsehoods. So it is something you have to trust. And it is quite difficult to trust a kernel, and in particular, you might want to formally verify it, and people are working on that. But in the meantime, you really want it to be simple as possible. Small code base, easy to understand, doesn't do anything crazy. In fact, John Harrison, I think, has a t-shirt where he has the code of the kernel of HOL on the t-shirt. And the font isn't even that small. So you basically have the whole code right here on the t-shirt. So if you're patient enough and don't creep him out, you can read his t-shirt and say, oh yeah, that actually does seem like a piece of code that does what I expect it to do, which is check proofs. All right, so the ideal implementation is small, all right, because you need to be able to read it and trust it. It needs to be simple because if it does anything crazy, like, I don't know, there are small pieces of C code that do incredible things, like solve the n-queens problem. Those are small but really hard to understand. And you also want it to be fast because you have all these crazy proofs that are, 100,000 lines long, and you'd like to be able to check those proofs without, having to leave it overnight on a gigantic cluster. In general, this small, simple, fast triangle is a choose-two situation, right? You can't have all three at the same time, as I'm sure you're aware in software development. You can't have something small, simple, fast. Usually, you have to give one up. All right, this is a pretty bad sales pitch, I have to admit, because Haskell often proposes to be all three. But in general, the pragmatics force you to sort of concentrate on two more than the others. All right. Okay, this isn't the slide I was expecting here. That's okay. So the logic itself that you're implementing is something that, yeah, you also need to trust to be consistent, all right? It's pretty easy to imagine a very powerful logic that is inconsistent. And a fascinating story that I'm not going to get into is that people have reinvented several times really great logics, beautiful, expressive, simple, intuitive, inconsistent. This is remarkably happened like 3 times, almost identically, almost identical stories where someone invents a logic, tries to think about it, gets really excited about it, publishes it, and then someone says, oh wait, here's a proof of false. Okay, so you want to find, something that's powerful but not powerful enough to prove false. And what we decided was to take something that has been relatively well studied but is still at the limit of the expressive power we know how to wrangle, is a theory of dependent types that somehow unifies function spaces, universal quantifiers, and polymorphism. I'm unfortunately not going into this because I think it's not an essential point that I'm trying to get across. I'm just trying to say this is the logic that we use. We could have used another one, but we use this one. An predicative type of propositions, a hierarchy of universes. Again, I'm going to skim over this. There are important reasons why you might want this, but I'm going to skim over this. Inductive families, which correspond roughly but not quite to what you call GADTs in Haskell. And something, and this is the real new feature, called quotient types, which really correspond to quotients in mathematics. And those are really useful. And this is similar to the core logic of the Coq theorem prover, if you've heard about that. Oh, by the way, I forgot to do this. Who here has heard of the Coq theorem prover? Okay. Who here has actually used it? Yes, he is also not the only person that uses Coq. But okay. So all right. So certainly Coq is very similar to Lean. So there's sort of a mental sort of barrier where Lean is, we're going to call it Coq++, but of course we're not going to do that. So the implementation in this triangle, small, simple, fast, we choose simple and fast. And fast is actually quite important. Coq has suffered. Coq was simple, small, and slow. And over the years, it's become huge and still, unfortunately, pretty slow. So the choice here was, okay, let's go for speed first, and we'll worry about size later. But we're still going to try and keep it pretty simple. It's in C++, and I can hear you groaning internally, so feel free to let that out externally. C++ is, of course, not a popular language. Yes?
Will it compile? Will it compile on the tested compiler, or is there things that would?
C++ is not verified, and it will never be verified. I'm going to make a grand sweeping statement that somebody is going to disprove in 20 years. C++ is the worst, all right? The worst language. It is impossible. Just to specify C++ is extremely hard. So the answer is no. There is no verified C++ compiler, and no, it's compiled with whatever you want to compile it with, basically, but mostly G++ and Clang. So it is very, very fast, almost staggeringly fast. And it's only 6,000 lines of code, which for C++ is really not that bad. And I think one of the nice selling points is that somebody else said, okay, let's see what we can do in Haskell completely independently. And they re-implemented a functional kernel in Haskell, which you can also find on the GitHub page. So if you want to read the kernel in Haskell, you can. Now, it is not the same kernel, but you can use it to check the proofs that the other tool generates. It is a lot slower, I have to admit. But it is simple, which is one of the nice selling points. OK. Let's see. Should we take a break, Gershom? Is everybody up to not taking a break, or should we take a break?
I mean, you could just keep going. If you want to stretch the lecture 5 minutes, and then you're going to come back and show some code.
Yeah, so right now I was going to show just code just to give an idea of what the specification language was. And later I was going to actually sit down and try and give a proof. But that's sort of more prone to error than just showing slides.
Could you just show the code at least? So
Yeah, of course. Yeah, of course. I've still got 50 minutes left, so there's going to be a lot of code. All right, so the statement I just wanted to specify is just there is an infinite number of primes. Pretty simple statement, pretty simple to prove. It's been proven in Lean, and the proof is not short enough for me to show you in a few slides, but the statement certainly is. So one thing that I think is quite beautiful, that is a complete consequence of the logic we chose, is that the logical connectives that you have built in, that are in the kernel, are the universal quantifier, which doubles as an implication, which is a nice feature of dependent types, and inductive families, all right? So inductive families are actually not that hard to specify, but they are the most complicated part of the kernel. So you have these three things, and what I say, and what I was surprised to discover when I was an undergraduate, was that everything else, every other logical connective most people could hope for, can be specified just using those things. In particular, inductive families is a really great way of writing down all the connectives. For example, the AND is just an inductive type with a single constructor that we call intro for convenience, that just takes a proof of A and a proof of B and produces a proof of A and B. And conversely, if you want to prove A or B, then you just need to prove one of them. So that means you just take two constructors, which is either I've proven A or I've proven B. And I'm doing this thing again where I'm putting the wrong one, aren't I? So don't worry about those curly brackets, though I'm going to try and explain them later. And of course, the trivially true proposition is an inductive type with just trivial as a constructor. And the trivially false proposition is an inductive type with 0 constructors, which, if you think really hard about what it means to be an inductive type and what it means to, say, prove something by induction over that type, this is really a correct definition. If you want to build something that is false, you take an inductive type with 0 constructors, and that is an unprovable statement, right? Because the only way you could really prove it was by applying the constructor somehow. Okay, so this is a neat trick. And then you just define negation to be implies false, and that works really well. Another neat trick is that with inductive families, now inductive types don't work anymore. You really need the families. You can define the existential and the existential quantifier and equality. And again, I'm not going to go into too much detail, except to say that this A right here basically represents the universe of things you're quantifying over. And because you never want to say explicitly, you just want the compiler to figure it out for you, we put these curly brackets around, which say exactly, you, type checker, try and figure it out for me. I'm never going to tell you what A is. You have to figure it out. And I'm not going to say much more about this, except this would be, an interesting point I could elaborate on. But you can just define what it means to be an existential proposition by using one of these inductive families. And even more clever.
Do you mind if I I'd like to try to pronounce that for people, because I think that for a lot of people, even what you've been explaining isn't quite simple enough, and they're going to find it sort of Greek, right? So just the exists one, if you don't mind if I jump in.
Yeah, go ahead.
Is good would be, we're going to say there's a type named exists, and it says for all A of type. So it says if it's generated by you give me a type, and then you give me P, which is going to be a predicate that sends that type to prop, which we can think of as either true or false, but as a proposition. That's not exactly right? But that's sort of, because when it says prop, you think of it as proposition and think of it as two inhabitants, true or false. So if to say something exists is to say, given a type, and given a predicate over that type that's true or false, then we may create a proof of the exists by using the for all symbol. That's just introducing the syntax there, correct? No?
Yeah.
Yeah. And so the constructor is actually that for all symbol. And it says,
I'm
given...
sorry, no, the constructor is called intro.
Oh, right, you're right, and then it's...
The constructor says you can take any A, that's what the for all says.
Yeah.
And if you give me any A and a proof that P holds for A, then actually, yeah, you've proven that there exists A such that P of A.
Right, sorry, so the for all we read there more like a lambda is how we would...
No, it's really a for all.
Okay, I'll let you...
Okay. It's saying if you want to prove that there exists an A such that P of A, all you have to do is give me an arbitrary A. That's what for all says. Really, give me any A and give me any proof of P of A. And then I've proven that, yes, indeed, there exists an A such that P of A holds. Okay, we're going to actually see an example of this statement at least. And again, this is sort of in detail, but it was to sort of motivate the fact that these inductive families are really powerful things. They allow you to say exists, and they allow you to say equals. Again, not going to detail, but that second line here is the definition of equality, which is quite nice. Of course, the thing we do right after defining equality is giving it a notation, which is less ugly, right? Instead of saying EQ AB, we really say, equal sign between A and B. And this is the most boring but also useful example of an inductive family. It's the natural numbers, which is just 0 is a natural number, and given a natural number, you can just take the successor. That is also a natural number. And now you can define addition and multiplication just by recursion, where you say, how do I add two numbers? Well, certainly if the first one is 0, then that's good, I'm done. And it's just the second number. And if the first one is a successor of a number, well, then the addition is, well, add the two remaining numbers and then apply successor to that whole thing. So this is kind of a classic example in defining things by recursion. It's how you define addition and multiplication. Yeah.
A bug there that the multiply 0 of m should be 0, not m.
Oh, yeah. Good catch. Sometimes I insert errors on purpose to try and get people looking. This was not one of those cases. Multiply 0 of m, of course, is 0. I'm sorry. This is mul m plus 1, I guess. And then multiplying can be done by recursively adding, of course.
So is this actually, I watch a little bit next to multiplication, is this actually what you're using? Is it a definition of natural numbers or is there some optimization?
The definition of natural numbers, yes. The definition of addition and multiplication, no, for sort of technical reasons, which is that the internal representation of these guys, these functions, is sort of decompiled. It uses something called iterators, which is a much more simplified and trusted version for the kernel. And so because of that, we sometimes use these iterations directly to define functions. And for addition and multiplication, yeah, it's the other uglier definitions, unfortunately, where we iterate successor and we iterate addition.
Does your kernel have some sort of special case for dealing with concrete representations of natural numbers, or is that not even right?
Oh, yes, it does. So if you want to write the number 5, which is on your keyboard, then yeah, the parser sort of knows how to say, oh, well, that successor applied 5 times to 0.
Well, the question is, do you end up manifesting it as 1, 0, 0?
Is it like Agda or not? Using a efficient representation?
It is not for NAT, but of course there is some other type called num, and that one is a binary representation.
So I have a slightly related question. Why aren't any of the
Built-in data structures in the universe applied correctly? At least in the standard time. Run into this a few times.
Yeah. So one of the reasons was at the time we didn't really see why they should be. And this is a complex question. I think that I can't really answer it right now. Yeah, I'd be happy to see that actually. And it's one of those things where I think the lean discussion group would be happy if you asked these questions because, well, they provide an interesting counterexample to the intuition that, oh, actually, there just needs to be one NAT instead of a ton of NATs that all live at different levels. OK, this is a technical question. OK, so of course, you don't want to write add an M unless you've grown up in the 70s at MIT. You want to write n plus m, and of course, lean is powerful enough to admit these notations. And same for equality, which I use right here. As you can see, I don't use EQ add nkm, as someone who does Lisp would prefer. So less than or equal is pretty simple to define once you have addition existentials. You just say, oh, well, n is less than or equal to m if there's some number that when you add it to n, well, it's m. All right? And division is very similar, but with multiplication, where n divides m. There's some k, and I think, no, this is the right definition. If there is some k such that multiplying n by k gives m, that's what division is all about. And then, of course, you can define what prime numbers are just by saying any divider is any divider that is, saying that a number is prime. There's this weird case that students never really understand why it's there, but mathematicians say, oh yeah, trust us, it's really important. P is only prime if it's greater than 2. That's just to exclude 1 as a prime. And P is prime if everybody that divides P is either 1 or P. And then, of course, what you really want to prove is that for any number, there's a certain P which is bigger and which is prime. And that, if you squint real hard and think about it for a minute, means that there's an infinite number of primes. That's usually what we take to be the definition of that statement. Yes?
You have a typo in your definition of prime there?
I'm sorry. What's that?
Try to parse the
It is there. I'm sorry. This is embarrassing. So this is a mathematical notation for divides. And I omitted the notation where I said DVD and M is actually N bar M.
Well, it's hidden under the 3 dots up there.
Yeah. It's right here. You see it? I'm
you crushed it really thin.
Yeah. I'm very sorry. This is standard notation to people that know it, and a very confusing notation to people that don't know it. So yes. So there is a DVD. It says that D bar P is DVD dP, which is better written than said. OK, so infinite number of primes you can express and prove this, and there's a quite nice proof in the lean library. Right, and here I'm sort of making the point about the elaborator, which is actually having these curly brackets where we say, oh, you try and figure what these guys are because I'm too lazy to tell you, is crucial. If we want to be able to write anything non-trivial, you really need those guys. Yes?
You have this thing where the file can follow along.
I'm embarrassed to say I do not have a file with the proof of infinite primes. It is in the standard library though, so if you dig a little in like the theories, number theory, it's going to be in there. The proof is actually written out. Yeah, so you really don't want to give all these things. This is extreme tedium for a human. For a computer though, it's not that trivial because substitution for equality basically says any property P for some type, okay, a property can be being prime, for example. That is a property of numbers. Any property P that holds of A, if A is equal to B, then certainly it should hold of B. All right? That's what EQ subst says. It says for any type, for any A, B, and for any property, then that last line holds. Again, extremely tedious to write this all out, but for a computer to guess what the values of A, little b, and P are, this is not trivial. In particular, P is a function, so, wow, I'm really going to ring that gong at some point. There we go. In particular, P is a function, all right? So to guess P, you have to guess what a function is. And guessing what functions are is basically what we all do for a job, right? That's what we do. So suffice to say, we do not solve this problem in general. But in practice, whenever you actually need to apply EQ subst, we have a very powerful engine that can fill in the blanks and try and guess a value for P. Wow, this is what my next slide was saying. For example, if P of A is the statement, and this is a little confusing because I'm using two equalities. I'm saying P of A is the statement A plus A equals 2, where equals is the proposition being equal to. So if P of A is this, then we have this, right? We know what this is, but it's not obvious what P is, right? It could be several things. In particular, the thing you all thought of is, oh, P is obviously the function which takes that something plus that something, and it says it's equal to 2, all right? That is a valid solution for this sort of question. What is P if P of A is this? But another equally valid answer is, oh, actually, no, it's only that first guy, that first x. It's, you take an x, you add it to A, and that is equal to 2. Or you could just say, oh, well, forget about the x. You take an x, you throw it in the garbage, and then you return this A plus A equals 2. So those three things are all possible. So in particular, the elaborator tries to find a P, but it can find several, and it needs to somehow decide which one it's going to keep. All this is explained in our paper, Elaboration in Type Theory. OK, now the proof language, and this is also an interesting discussion which I'm going to have to sweep under the rug a little bit. The proof language is an extremely active area of research. We do not know how to design a language that is powerful, that allows you to express proofs of propositions. We've been trying for very long, and we've been starting to make the same mistakes that all language designers make. And we've been through these mistakes, the modularity, the lack of readability, the ability to use code as an expression of intent rather than just an expression of what the machine is supposed to do. All these language design problems that computer scientists have had, now people in interactive theorem provers in the ITP community are having them again and solving them again. But there are sufficiently different problems, unfortunately, for the solution to not be obvious, even if you know what a programming language should look like. So right now, to simplify things a lot, there are sort of two main currents of how you should be able to describe a proof to a computer. One is what we call tactic languages, which is a very operational way of seeing things, which says, OK, now apply this lemma, now clear this hypothesis. And if any of you has ever used fourth. Has anybody used fourth here? Wow, more than I expected. Wow, that's surprisingly more than I expected. All right, how would you qualify the readability of a fourth program?
Easy it is.
Better than C++. Okay, so a pretty low bar. So I would say that stack-based languages are not great for readability. And tactic languages are basically stack-based languages. What they say is, here is a number of things I want to prove. Each command takes one of the goals or several of the goals, does something, and replaces them with one or zero or many new goals. Okay? So at each point, you have a stack of remaining goals, and each tactic sort of pops the stack, does something, pushes a bunch of new goals. Ideally, that new goal is simpler, and eventually you sort of pop the whole stack and end up with 0. And once you've done that, you've proved your theorem. It is extremely fun, and it is rather intuitive for a computer scientist at least, really not for mathematicians. It is extremely hard to read. The Isar-like language, for lack of really a better word, I would like one, is more declarative, where you say, this is what I want to prove, now assume this, now you get this, now apply this lemma, and you get this. And so it's much more declarative. It's really verbose. It is much easier to read, especially to mathematicians. On top of this, of course, you don't want to prove everything. You don't want to explain every little detail of a proof, and so you need proof automation. Lean right now is weak on the proof automation side. Okay, now has come the point where I thought I'd have an hour and a half left. I would have been terrified to have an hour and a half left, but half an hour is almost equally terrifying. But we're going to try and work through some simple examples to actually see sort of what this is in the flesh. But it is really a good time for questions right now if you have some sort of more elaborate questions.
Andy, if you set up on the computer to help follow along in real time,
Yeah, of course. I'm not going to sit in a corner and do this. I'm going to do it on the big screen, and you'll see it looks, if I can get it right, it'll look great. If I can't, it'll look terrible. So we'll see.
So the impression I'm getting from the presentation, and correct me if I'm wrong, is that there's a focus on intuitionist mathematics, where
So intuitionism, mathematics, and the Curie-Howard isomorphism are related but not interchangeable. It's true that it tends to come up naturally, especially for computer scientists. Lean isn't tied to that. In fact, when we started Lean, we were completely committed to the idea it would be completely classical. It turns out that because of how powerful our type classes are, we didn't need to do that. Surprisingly, every time we wanted to sort of say something about the excluded middle, the things we were talking about were decidable. And so we have a decidable type class, which is kind of nice. And then if you want to assume the excluded middle, then you just say, oh, and actually everything is decidable. I'm sorry. I kind of interrupted you before the end of your question.
that was actually the question I was coming around to. How do you consider a classical?
Yes. And in fact, for a lot of things, including a lot of analysis, people don't really know how to do things intuitionistically very well. So in general, the first thing you do when you're formalizing calculus and analysis is assume the excluded middle. And there is a library of analysis, and of course, the first thing it does is assume the excluded middle and some other thing called the Hilbert choice principle, which is a little bit more technical, but yeah. I'm sorry. The good old completeness theorem. So I know what the good old completeness theorem says. It basically says, here's syntax, and here's the semantics, and somehow they agree. And I'm not sure I understand what the rest of your. So which problems specifically are you looking to solve? Yeah, so Gödel's completeness theorem is quite useful, for example, when you're trying to choose a logic. Gödel's completeness theorem says, oh, this logic is nice because it says everything you sort of want it to say. It can prove all the theorems that you want to be true. Unfortunately, it doesn't really hold in higher order logic. So in general, you sort of have to give up completeness. So you usually work with logics for which the standard interpretation is not complete. So you do give up completeness, but in general, completeness is a nice theorem, but it's not a necessary theorem just to do formalization. When you just want to do formalization, you just want soundness. You don't care that much about completeness. Oh, Lean uses both, which is kind of nice. What's that? Yeah, you have a choice, and not only do you have a choice when you start proving the theorem, you can interchangeably flip between the two choices in the middle of a theorem that you're proving. To a certain extent, it's a surprisingly lightweight feature in the sense that the is-are-like language is surprisingly easy to support if you have a simple language. You sort of you add a little syntactic sugar and you get an is-are-like language.
What is part of my ignorance? What is this?
I'm sorry, is-are is a proof language that is used in Isabelle. And it's called is-are because it is inspired from the proof language of Mizar, which is another interactive theorem prover. And do not ask me why it's called Mizar, because I have no idea. So yeah, Lean is sort of unique in that sense, but it's actually, it wouldn't be that hard to add it in other languages, this sort of flip between the two styles. And in fact, don't take my word on it. Isabelle might very well support this move between the two styles. It's quite convenient. Sometimes some things are just nicer with tactics, especially short proofs. Any other questions? Okay, so this is not an invitation to stop asking questions, but I'm just gonna slowly move to here. And all right, so there's something called lean Emacs. And basically it was just simpler to introduce a new command than to configure Emacs to automatically know if it was being called. In fact, this is really a testament to Emacs to sort of how powerful it is to develop one of these interactive theorem provers. So this is completely incremental. So I can write foo here, and FlySpec comes and says, oh, you made a mistake here. I don't know what foo is. You made a mistake. And so this is one of the nice things. It's not something that is easy to advertise when you're a theoretical computer scientist, but this interface is really neat. It heavily borrows from the Agda interface, so we're really indebted to Agda. And Sunho is a genius in the Emacs version of whatever scripting language they use. So I'm sorry. All right. So the first thing we do is import a bunch of things. The things we import is facts about logic and facts about logical connectives. I'm not sure I'm going to be using any of these because for the purpose of the tutorial, I'm going to reprove things that are in the standard library. And I'm even going to be sitting down. So, okay. So you import these things, and then you're completely confused. If you want to use anything from logic, you have to sort of say logic dot, or there's the notion of namespaces where, maybe you'll see it more later, but where everything lives inside its own namespace, and it works like almost every language except Haskell, I guess, even Haskell, where you type namespace dot and then the name of whatever thing you want, actually. And if you don't want to type that, then you open it. You open the namespace, and then you don't have to type the thing dot name of my theorem. Now, a really useful thing to do is type help commands, which just lists all the possible commands. Can I do this? Yes. And here's just the list of all possible commands you can write at the top level. One of them is section. One of them is parameters. So this is quite useful. So I'm going to create a new section, which just basically says, OK, I get to declare new types and new propositions and assume things. And once I close the section, I'm going to stop assuming all those things. So in particular, I can say assume the excluded middle. And once I close the section, it's going to forget that I assumed that. So I create all these abstract propositions that I call A, B, C, D. I'm going to prove a bunch of things which are just going to depend on these parameters. And when I close the section, this is kind of neat, it's going to universally quantify over all the parameters. So this left distrib here, this says something about a certain equivalence between things. Once I close the section, this lemma is going to say for any A, B, C, and D, this proposition holds. Okay? So sections are quite useful for this kind of thing. You just sort of say, fix these guys. Now I'm going to assume that they're fixed. But once I close the section, you can remember that I didn't assume anything specific about them, and you can quantify over them. OK, now I'm going to say something about a logical equivalence, which is just if and only if. And if I hover over it, you can see that it takes two propositions and returns a new proposition, which is kind of unsurprising. And it just says what the distributive property says, which is A and B or C is equivalent to A and B or A and C, which is something we all sort of intuitively know, but is one of the first non-trivial things you might want to prove in logic. OK, now, unfortunately, if I want to prove anything, I'm going to have to use certain facts about this guy. All right? Either I'm going to have to unfold the definition, or I'm going to have to do something. And I don't even know what that thing is called. Now, something that does not exist in Coq, and I really wish it did, is this print notation guy. So let me delete it so I can sort of show how the input works. This is really borrowed from Agda, but I think it's brilliant. Is print notation and then backslash if and only if, and that works. Apparently, yes. Takes a few seconds. And this will tell me, oh, this symbol you just typed is defined somewhere, and here's the way it's defined. And this is a hard-to-read definition, but ignore the :20s. It basically just says that this double arrow is just defined to be the function IFF. OK. Now, the next thing you want to do is say, well, what do we know about IFF? Now, conveniently, IFF is also a namespace, so you can just say print prefix IFF, and it will print every theorem which starts with the namespace IFF. And there's a bunch of them, which basically say most of what you could hope to say about if and only if. Maybe not. So the one we're really interested in is the definition, which is right here, iff.def. And iff.elim is not bad either. It's the two directions you really want. You want to be able to say, oh, how do I prove an equivalence? Well, I prove an equivalence by proving one direction and then the other direction. And how do I use an equivalence? Well, I kind of prefer the ilim left and ilim right. And ilim left just says, well, if you have A, if and only if B, and you have A, then you have B. Same for the right. OK, so now we kind of know what we're dealing with. And here we say sorry, which is a really convenient macro, which just says, I'm sorry, I give up. But we're going to try and do better than this. So one way to start a proof is just say proof QED, and then underscore this. And the underscore says, oh, I don't know what to put here. You try and figure it out. And whenever you do that in a proof, Lean says, I really don't know how to figure this out. But here's the type of what I tried to figure out. And this is something I wish I had in Haskell, where you just say, oh, I don't really know what to write here. I'll just put an underscore. And I want the type checker to tell me.
We have that now.
Oh, yes. OK. So this is, use this feature. It is fantastic. Yeah, I admit, I actually had heard about this. I just haven't. OK, so we want a proof. So what are we going to do? Well, we're going to try if and only if. Oops, touch screens. I feel old because I'm really not used to touch screens. So I want to use if and only if dot intro, because that certainly is what I want, right? Is to prove an if and only if. And if and only if intro, and then I say, oh, I know it takes two things, right? Because it takes a proof of the left-hand side and the right-hand side, but I don't know what to put here yet, so let's just put underscores. And Lean tells you, oh, here's what you should be putting instead of these underscores. On one hand, a proof of the left-hand side. I'm sorry. On one hand, the proof of one direction, and here, of course, the other direction. OK, so what I often do here, in proof mode at least, is, oops, I have to admit, I often forget the syntax for proofs, which means that I have something that's quite useful, which is a quick reference, which tells me a few things. In particular, if you're in what's called term mode, which is what I call the isar mode, here's all the things you can say. And it's not all the things you can say, but it's a very convenient list of things you can say. And one thing I want to say is assert the first thing I want to prove, which is A and B and B or C implies whatever's on the right, which is A and B or A and C. And I'm going to say from this, and I'm going to give it a name, and I think the name I'm going to give it is H, because I'm not a very imaginative person. And then here, what I exactly want is H. OK, great. So I've done one thing. Let's do the other one. Let's call it H prime, because I'm still not imaginative. Let's copy paste, because I'm lazy. Still don't know what this proof is going to be, but certainly it goes here. All right, so now I'm done with the proof, except these little two details, which are here and here, which you'll notice are exactly what I didn't have earlier when I applied if and only if intro. But at least I'm sure that that line, if and only if intro, is correct. Because if it wasn't, if I had something wrong of the wrong type here, it would complain. In particular, if I delete this, It doesn't complain. It would complain later. I'm sorry, this is a little embarrassing. Yeah, for example, if I have this, H and H, it's going to say, oh, well, that's not great because H has this type and it's expected to have another type. Sorry, this is a frustrating side effect. There we go. H has this type and it's expected to have some other type, which is the usual typing error you get in Haskell, but here it's telling you that you've proven the wrong thing. Okay. Now let's prove this. So what are we trying to prove? We're trying to prove this implication. Now the first thing you always do when you have an implication is you assume something. Still no imagination. And you assume the thing that's in the left-hand side of the implication, right? This is the first step when you prove an implication. If you want to prove that A implies B, you say assume we have A, and now I'm going to show you that B holds. All right, so we assume this, and now all we have to do, and it's here at the bottom behind the turnstile, is prove this second part, which you'll notice is, of course, this, which I've unnecessarily parenthesized, apparently. Now, sometimes it's useful to remind yourself of that, so you might want to say, show A and B, or A and C, from what I'm about to tell you. And to do this, well, I need to somehow use the fact that I know that both A holds, because H1 says that certainly A holds, and I also know that B or C holds. So how do I do that? I say obtain I, or I'm sorry, let's call them L, and R, from H1, and I'm sorry, this is a little bit confusing because of the because of the way my Emacs is set up. It's saying, oh yeah, L and R, you've done everything right. You had a conjunction, A and B or C. You said obtain L of type A and R of type B or C, and now you have those. Now you have those things, and you can use them to finish your proof. Now the rest of the proof is going to be a case distinction on R. Okay, so R says that B or C holds. I can certainly suppose B holds, show my conclusion, and then suppose C holds and show my conclusion. And to do that, I can't remember how, but I can say print prefix or, and it will tell me. And it will tell me that to do that, I need to do a cases on. All right. I could also do a elim and a by cases. This is yeah, I seem to be out of power also, so.
So you're not getting charged? Is that why it went off? Or
No.
Is it a cable problem?
It's a cable problem, I guess.
The cable is running all the way back and it's plugged in there. So there has to be a problem on the pickup side.
I'm sorry. I can. It won't be very fascinating. I can use or.cases on, and I just write it down, and then I have two similar goals, which are quite simple.
Let me try the other table, just in case that one works better.
Yeah.
Try this one instead.
Oopsie.
I think something came loose on that side.
Yeah, so I mean, the main takeaway, I only have a few minutes left anyway, is you should try Lean, and you should try the Lean tutorial, which is quite nice. There's actually a tutorial online. So there's a JavaScript front end for Lean, and so you can just go in your browser and do exactly what I'm doing right now and have the same interface as what I'm doing right now with this sort of, underline your errors as you type, which is sometimes annoying, but quite convenient once you get used to it. And you can work through this tutorial where an almost identical goal will be something that you're asked to prove, and you can try it out, and you can sort of, if you have more advanced knowledge, you can try, do whatever you want in the browser, and if you're not a fan of the browser, then you can just download Lean and do like I did with the Emacs mode. It's standalone. It's really well packaged, I believe. And I had a really, really long example that I now cannot believe I thought I would have time to show you that shows you some more of the power and some nice features of the tactic mode where there's sort of...
Is that thing coming up, or is it working? Is it going to work? No.
But we got 5 minutes left, so
All right, so I can gesticulate for 5 more minutes, or I can just ask you if you have other questions.
My question would have been, if I were just to look at this as a piece of mathematics on a printed page, how would I go about, in what order would I be reading this thing? Up, down.
Yeah, so the ISAR proof is really supposed to read as much as possible like a mathematical proof, where you say, oh, assume I have this. I'm going to show this.
Like he goes, okay, from
Yeah,
this,
the from is not an ideal keyword, I have to admit. Maybe there's from. I'm sorry. From is just a keyword. Usually, it really makes sense when you say show this from, and then you write down a proof. And so from says, from this argument, you can show this. It doesn't have to make that much sense.
Slightly backwards from what I would do.
Yeah, I guess. I mean, it's often useful to stop in the middle of a proof and say, oh, here's what I have left to show.
Yeah.
And then continue the proof. You could imagine a billion macros that are just sugar, where it says, oh, it suffices. And some languages have that, and you could make a case that Lean should add those. And if you want to make that case, then use the Lean user mailing list. But for the most part, yeah, this assert assume, it's supposed to look somewhat like a mathematical proof. It doesn't really look like a mathematical proof. It doesn't take very much to get used to it. And then the tactic mode doesn't look anything like a mathematical proof, but it's quite fun and it's quite easy to get used to, because basically you're looking at your goal and you're doing things step by step and you're just knocking away at the goal. And when you finish, it's this fantastic feeling. It just feels great, much better than programming, in my opinion. Yes?
So if you've convinced me that I'm nowhere near smart enough to sit down and start playing with this,
That's the opposite it's really the opposite of what I wanted to do.
what times I can't even figure what braces are. The question I have for you is how do you get started? You tempted me. I want to learn this stuff. Are there books?
So for Lean, read the tutorial that's online. That is the reference. It is also as a PDF form. Read the PDF. Jeremy Avogat is one of the great sort of pedagogists of his time. He explains things very well, and he mostly wrote that along with his students and Leonardo Mura. Read the tutorial, try to work through it. That is my recommendation.
Can I ask something to that?
Yes.
Just to add to that, if you go online, not only is the tutorial a book, it runs Lean in JavaScript in your browser. So you can actually, without installing a thing, without installing Emacs, the simple examples that work relatively fast, you can type along just using the web, which is the first that I've seen any Theorem prover do that. So it's very accessible.
Yeah, I did already mention that, so that's maybe why it took away your impact, maybe. And if you have questions, you can come and see me in the next few minutes, and you can also write to the Lean user mailing list. And people are pretty nice there. They'll answer your questions. Yeah, so the main disadvantage Lean has is lack of automation, which we're trying to fix right now. And by we, I mean they. I wish I was working on this, but right now the Lean development team is really trying to fix the lack of automation. And I mean, these are complex pieces of software, so listing the ways in which they're identical and different would actually be quite a task. In general, no two theorem provers are exactly alike. Really what you want is a large library and lots of automation. And so that's what Lean is aiming for right now. It has a reasonably large library actually already. It still suffers from the lack of automation. But the elaborator and the proof tactics are really nice. And so those are positive points. You don't need to worry about the foundational issues so much. Those are details.
What exactly do you mean when you refer to libraries with respect to
So they're really like libraries for programming language, yes. So it's a bunch of theorems, like hundreds of definitions of statements and theorems. And when I mean hundreds, I mean tens of thousands.
and how do you search for something?
Well that's a good question. Usually this print prefix is quite powerful. You can also just browse them. Like the libraries themselves have markdown files that sort of say, oh, and here's each file, it contains developments about this or that. And then a feature that Coq has that we don't have yet is try to pattern match against something and bring up all the theorems that match this expression. I'm not sure that's as useful a feature you might think it is, but you can do that. Because in general, your statement matches over 1,000 theorems in the library, maybe 10,000 if it's a big library. So usually what you do is you look at the definitions, you look at the right library, and then when you forget the name of a theorem, you just say print prefix with the right prefix, and the theorem you're looking for is in that list, and it's only going to be a list of less than 100 things. Reading the libraries is actually something that is still sort of a de facto standard for theorem provers, unfortunately. Yeah, it's a hard problem actually. I think it's still a research problem how to sort of find the right lemma for you. If it can be found automatically and applied automatically, then that's great. But usually it can't. Usually you need some hints. So how do you search for that hint? I don't know. I mean, I feel like this might be a problem you have in Haskell too. I mean, if you're looking to see if a function exists and is implemented, I mean, admittedly, Hugel is fantastic, but here, Hugel, it's not clear that it would work as well.